In this video, we'll be talking about how to find the derivative of inverse trig functions. So we can use the rules below to find the derivatives of inverse trig functions. And just take a note that these functions might be noted as, for instance, inverse sine of x with that -1 exponent notation for inverse, or it could be arc sine of x. And that's just using sine as an example. That would apply to any of the 6 trig functions. All right, what we're going to notice looking at these is they look quite complicated, these inverse trig derivatives, but there's definitely some little shortcuts we can notice here in order to help us out. Similar to when we've learned about trig derivatives, if the function you're taking the derivative of starts with this c, they are all negative. And you'll notice that some of them are the same otherwise besides the negative. So sine and cosine actually have the same derivative, or inverse sine and inverse cosine, except cosine's negative. Same with tangent and cotangent, and same with cosecant and secant. Cosecant and secant, those inverse trig derivatives are much rarer on tests. So for instance, if you're taking AP calculus, those are pretty rare to see on the exam. Okay? The other 4 come up much more frequently. All right, so let's try some practice questions. What I would suggest is having these 6 derivatives written down. So if you need to pause the video, have them written down so you can refer to them, take a screenshot. But we want to be able to refer to those derivatives throughout the video. All right, so number 1 says we're going to find the derivative of 2 inverse sine of x. So what we're going to do is we're going to find the derivative using our reference above here. So that's 2. I'm going to keep the 2 as it is, times 1 over 1 minus x squared inside the radical. And we could simplify that if we want and just put the 2 on top. Number 2 is looking for arc cosecant x, the derivative of that. That's the same thing as inverse cosecant. So this one I'm going to just copy exactly from my reference chart above. So I have negative, remember it starts with a c, so negative, 1 over the absolute value of x times square root of x squared minus 1. Number 3, we're taking the derivative of inverse cosine of 5x. Notice it's not just x here, so this means that this is going to have an application of the chain rule. So let's carefully think about what this is going to look like. So we know the derivative is negative 1 over square root 1 minus, but since this question's not x, it's 5x, it's 1 minus 5x squared. But we have to multiply that by the derivative of the inside, so times 5. And here's what our answer looks like. Okay, you could choose to simplify that in the denominator if you'd like. I'm going to leave it just like this. Focus more on the derivative part rather than the algebra simplification in this video. Number 4. Rather than look at this as a quotient, I'm going to pull 1/7 out in front as a coefficient. I think that's a little easier to look at. And now I can take the derivative. Keep the coefficient. The derivative of inverse tangent is 1 over 1 plus x squared. And if I want to simplify that, that's 1 over 7 times 1 plus x squared. Okay, let's take a look at some more. G of x equals arc sine of 3x squared. Notice this is a chain rule problem. Anytime it's not just x, we're going to have to use the chain rule. So g prime of x equals, I'm going to look at my reference and I'm going to see, well, what's the derivative of sine, inverse sine, excuse me. And that's 1 over the square root of 1 minus 3x squared times the derivative of the inside, which is 6x. Okay, if you'd like, you could put 6x in the numerator and make it one single fraction. Number 6 is an example of this is not a chain rule problem because we only have x there. We don't have 5x or 3x squared, something like that. So I'm going to keep my coefficient of 6, multiply it by the derivative of inverse secant. That's 1 over the absolute value of x times the square root of x squared minus 1. And again, if you want to simplify that into one fraction, you can. Number 7, this is going to be chain rule because I have an ln of x in the inside. So the derivative of cotangent is negative, starts with a c, so we need a negative, 1 over 1 plus whatever we were taking the inverse cotangent of, so ln of x squared, times the derivative of the inside. The derivative of the inside is 1 over x. Okay, the derivative of ln x is 1 over x. Number 8, also chain rule. When we go and take our derivative, the derivative of inverse cosine is negative 1 over the square root of 1 minus whatever we were taking the inverse cosine of, so 1 minus e to the x squared. And it's chain rule, so derivative of the inside, the derivative of e to the x is simply itself, so times e to the x. Number 9, another chain rule application. That's because we have arctangent of 9x here. So taking the derivative of arctangent, remember that's the same as inverse tangent, is 1 over 1 plus whatever we're taking the arctangent of, so 9x squared, times the derivative of the inside. In this case, the derivative of 9x is 9. Number 10. Looks a bit more complicated, but it's kind of just a combination of other skills we've practiced in this video. We're going to take the derivative, keep the coefficient, so keep -2. The derivative of arc sine, remember that's the same thing as inverse sine, is 1 over the square root of 1 minus whatever you were taking the arc sine of, so in this case, x cubed plus 5 pi squared. And since this is chain rule, we're going to multiply by the derivative of the inside, which is 3x squared. Notice 5 pi is just a constant. That's just a number, so the derivative of that is 0. That's why it looks like almost that term is disappearing when we go and take the derivative. If you wanted to simplify this one, we certainly could combine things here. The -2 and the 3x squared, for instance, can give us -6x squared. All right, let's take a look at 2 more. Number 11. This one definitely looks more challenging. I noticed there are 2 sets of parentheses. So this is going to be an example using double chain rule applications. Okay, so let's try and go slow and keep track of our work. The derivative, we're going to bring down the coefficient of 4. The derivative of inverse sine, we're looking at our reference sheet here, is 1 over the square root of 1 minus whatever we were taking the arc sine of or the inverse sine of squared. And now we have to multiply by the derivative of what was inside there. So the derivative of cosine 2x is negative sine 2x, but I have another chain rule application there, so times 2. Since I have so many terms here, I am going to clean this one up a bit, and I would get -8 sine 2x over the square root of 1 minus cosine 2x squared. All right, last question. We're looking for the arc cotangent of the square root of 3x. If I rewrite that here, when you are taking a radical, that's the same thing, or a square root, that's the same thing as raising to the 1/2 power. And you can see I have 2 parentheses here. So just like the previous problem, this is going to be a double chain rule application. All right, so let's take our derivative. The derivative of f of x is going to be -1 over 1 plus whatever we were taking the arc cotangent of, so radical 3x squared. And we're going to now multiply by the derivative of radical 3x. Okay, I would bring the 1/2 down, subtract 1 from the exponent to give me negative 1/2. And there's my double chain rule. And here I've got to also multiply by the derivative of the inside, which is going to be 3. All right, if we wanted to clean this one up here, notice you have in the denominator here, radical 3x squared. That's just going to give me 3x, right? The radical, the square root, and the squared are going to cancel each other out. Times, this is going to be 1 over 2 radical 3x and times 3. And if I put that all together, I'm going to get 3 over 1 plus 3x times 2 radical 3x, and that would be our derivative.